Okay, so Liam.
Thanks, Robert. Thanks a lot for the invitation. It's a rare privilege to be able to address a particle theory group. And I have something that I'm excited to talk about that I think has more overlap perhaps than I typically have had with the sorts of questions that you folks might care about. So here's an array of my collaborators on this work and some related works. And as we go through, I'll talk about which particular papers various people have taken part in. And many of these collaborators have actually joined this call. So, okay, in summary, what we do is construct a landscape of vacua of string theory and study the resulting ensemble of four-dimensional effective theories. And one of our main findings is geometric hierarchies. Hierarchies that are powers of the number of axions, which I'll call n throughout the talk. And these geometric hierarchies lead to similar hierarchies in the low energy couplings. So that's where this geometric finding has some relevance. And one consequence, as I'll explain at the end, is that the Peccei-Quinn mechanism automatically solves the strong CP problem. The Peccei-Quinn quality problem, which I'll review, is automatically solved. So a few words about the general goals. I'm going to call it QGEFT. I'll use that term to describe the low energy effective theory in four dimensions that results from a true ultraviolet completion of gravity, such as a vacuum of string theory. And I don't mean sort of string inspired, but we really like to understand the properties of the theories that result from actual vacua. So that's what we're driving at doing. And we'd like to understand some of their general properties. And you might try and figure out beforehand which properties are going to be worthwhile. What do you hope to learn from this? So one claim that's been rather too much used of late is that not everything is possible in quantum gravity, and there are major restrictions. But this has a sizable kernel of truth. There really are some broad patterns that are dictated by the structure of the UV theory, for example, as I'll show today, by geometry. And those are the patterns that we'd like to figure out. So first, a pretty basic lesson of the last 35 years or so of studying string compactifications. Topologically simple compactifications, that is to say, compactifications in which the topological numbers are not large, they yield simple QGEFTs. So by simple QGEFTs, I mean there aren't any large dimensionless parameters, and so naive dimensional analysis works quite well. And since we're coming from a UV completion of gravity, we can certainly ask about the properties of Planck suppressed operators. And by simple EFT, I mean the Planck suppressed operators have the expected size. So if I have some dimension delta operator O delta, then the Wilson coefficient C delta sitting out in front of it will be typically of order 1. Now, it doesn't mean always exactly order 1, but in that general realm and not parametrically different. But all of this is coming at the level of sort of assume a spherical Calabi-Yau. And the point of this work and this talk is to go beyond that and ask about more details. So what if we're facing a topologically complex compactification? And by complex, I mean something precise, which is that some of the topological integers are large. So the number of cycles of some kind is large, or some intersection number is large, or some other invariant is a large integer. A large integer is a large dimensionless parameter. And we should ask how naive dimensional analysis gets made less naive in the presence of such a large number. So suppose we have some large integer n showing up in the topology underlying some theory. Well, sometimes a coefficient that you might have thought would be order 1 becomes order n. Maybe not such a big deal, but sometimes it becomes e to the n, or even e to the n squared. And as an example, suppose the operator in question, so I apologize for the fact that curly O is both used for order of magnitude and operator on the same slide. It's different, those two different meanings in these two bullets. Suppose the operator in question is the mass matrix, the set of masses for a collection of N-axions, phi I. The truly naive treatment would be to say, well, there's maybe one scale in the theory. Let's suppose all the axions have about the same mass. That would be treating the eigenvalues of the matrix as being all the same. And that's just too simple in general. The point of random matrix theory is that that's too simple. One doesn't just have eigenvalues all piled up in one place. They spread out, they're correlated. As an example, the probability of fluctuation to positivity in the famous Gaussian orthogonal ensemble is e to the minus n squared. So that's something where you couldn't just make an estimate correctly by assuming all these variables are independent numbers, all of the same scale. Now, I don't want to get too carried away with random matrix theory. The talk has very little to do with random matrix theory, but that's just an example that illustrates that when there's a large-ish number, by large today, I mean 10 to 100 to maybe 400 sometimes. When you have a large number around, sometimes it doesn't enter in a completely obvious way, and you should revisit Wilsonian thinking in view of factors of that number. Okay, so how can we incorporate these kind of effects? Well, a very conservative, you might even say too conservative approach is just to charge right in and try and find solutions of string theory where there are large topological integers and see what falls out. So just find some vacuum of string theory and study the QGEFTs that result, and then see where do the powers of n go in the Wilsonian theory. Okay. Now, a problem with this is that until recently, topologically complex compactifications, those with n, a large number, so with a large number of moduli or axions, were just too complex to analyze. It's been well known that they exist, but the computations to try to figure out what the topological invariants really were intractable, even for specialized computational geometry software. So if you take off-the-shelf software like Sage or Topcon or Instanton and you try and compute some of the data in these geometries, the costs are exponential in the number of axions, and that's just brutal.
But Liam,
yeah,
sorry, could you not like start with relatively small n's, but look at it as a function of n and try to make some guess for how it was growing? Or
yeah, absolutely. So absolutely you could, and in fact, this is what people did. The trouble is, so okay, what I'll describe is a case in which the key number, the number of axions n, ranges from 1 to 491. Okay, and so 1, 91. And it turns out that these things, these off-the-shelf pieces of general purpose computational geometry software can go up to about 4.
Yeah.
And the extrapolation is just not a very good extrapolation. That's the problem.
Fair enough. Yeah.
So when we couldn't do any better, that's exactly what we did. But there's some other things where you need to get your hands on the complete story, and it's not possible down there. Yeah, good. Okay, great. Other questions and comments now. Okay, well, we've overcome this problem. We've been working on it for a while. Here are some of the papers we've written in attempting to tackle it. And what I mean by overcome is just that we've found essentially polynomial time algorithms for everything, all the key steps, and implemented them in a software package, CY tools, which stands for Calabi-Yau tools. Now, this talk is not about that. Okay, I won't be saying very much more about computational geometry. I do want to give you a bit of a picture of the story or the fun part of it, but it's just for context. For the purpose of this talk, we should think of CY tools as an oracle that produces Vacuoah string theory, and we just want to understand the outputs of that oracle, not the makings of it. It might matter a little bit where we're looking, and I should specify we're looking under a particular lamppost, type 2B compactifications on Calabi-Yau hypersurfaces. So that's certainly not the only solution of string theory. Very far from it, but it's the solution where we have the best control of certain kinds of topological data, and that's why we're looking there. Now, if you study a compactification of type 2B string theory, say, or any other string theory at weak string coupling, and in which the radii of all the cycles inside the space are big in string units, then what you have in hand is a weakly coupled UV completion of gravity. It's weakly coupled because the two weak coupling expansions, the string coupling expansion and the curvature expansion, have small expansion parameters. So it's a UV completion of gravity, but one in which the quantum gravity scale is actually parametrically below the Planck scale. In fact, it's the string scale, which is somewhere further down. So that's the piece of control that we have in hand. Okay, now this is under a particular lamppost. Many of our results do plausibly apply to other classes of, let's say, Calabi-Yau compactifications. To even broader classes, I dare not guess whether they apply or not. But we'll see at the end what you might try and guess. Okay, so now having given the context, I can give the summary again, but in more detail. So what we really do is we construct a landscape of Vacuoah string theory in type 2b flux compactifications on Calabi-Yau threefolds. And we study the resulting ensemble of N-axion effective theories. And this is an explicit incarnation of the string Axiverse. And we'd like to understand some of its properties. Now, a null hypothesis that you might make about such an Axiverse is, let's assume the internal space is just isotropic. It has one length scale, call it L. So the Calabi-Yau is roughly spherical. And we refute the null hypothesis. We find that there are actually hierarchies of cycle sizes. And those hierarchies are powers of the large number n. So we've got some teeny tiny cycles, some medium-sized cycles, some gigantic cycles related by powers of n. And so in one sentence, our finding is that topologically complex Calabi-Yau compactifications are anisotropic. They have small regions and big regions. And this has a consequence in the 4D theory. It leads to distinctive distributions of the couplings of the axion decay constants F, the axion masses M, and then the instanton actions S. And so part of the work is going to be to characterize those distributions and see what kind of physics they tell us. Okay, and then to finish the summary of what I'm going to say, we apply this then to strong CP. So you may know that the Peccei-Quinn solution of the strong CP problem is sensitive to Planck-scale CP breaking effects. And so it really requires UV completion. Planck-suppressed operators, as I will review, can completely spoil the Peccei-Quinn solution of the problem. This is what's called the PQ quality problem. It's a UV sensitive problem. Now, in our ensemble, where we actually have quantum gravity theory that's weakly coupled, the CP breaking comes from certain instantons, which we can enumerate, whose actions we can compute. And what we find is that when the number of axions is about 20 or more, the Planck scale breaking is just negligible and strong CP is solved by Peccei-Quinn. Okay, so bottom line, the Peccei-Quinn quality problem goes away when the number of axions is bigger than about 20. Okay, so just a remark or other piece of context, we've recently used the same computational tools, many of the same collaborators, to find supersymmetric ADS4 vacua along lines laid out by Katsuru, Kalash, Linde, and Trivedi, in which the vacuum energy is exponentially small. These are ADS vacua, so the vacuum energy is negative, but its magnitude in some cases is less than 10 to the minus 123 in Planck units. So we think this is a pretty exciting result, but that's not the topic for today. I'll talk about these vacua in the October 18th SATP colloquium. And let me stress that despite the overlap to some extent of people and computational methods, the physics is different today. It doesn't make use of these ADS vacuum constructions.
Sorry, just to ask a question at this point.
Please.
This is possibly somewhat naive, but yeah, you have these vacua that you're looking at, and presumably, can you say anything about the vacuum energy situation there?
Yeah. What I am not yet doing, so okay, although we have recently made progress as indicated on this slide in finding vacua with all moduli stabilized, we have also recently made progress in enumerating Axiverses. We haven't merged those two things. So in the solutions of string theory that I described to you today, there will actually secretly be a moduli space for the saxions, for the real part moduli governing sizes of even dimensional cycles. And we expect that in the fullness of time, one can understand the stabilization of moduli in those cases. You might say, well, how can you even talk about them if you haven't dealt with the saxions? Well, the axions are protected by shift symmetries and the saxions are not. And so it makes sense to describe the properties of the axion effective theory rather separately. Now, if your question was, can we take these vacua in which the CC is small and discuss the axions there? We certainly can, but I don't have statistics to report to you. Was that the nature of the question?
It was more like, so with these things, would saying, okay, we need to be able to make the CC small, like change the way you're discussing? Would you expect that these conclusions that you're going to give do or do not manage to carry over?
Yeah, right. So here, the problem is the following. This is an excellent question. Let me open a brief parenthesis to answer it and then close the parenthesis. Okay, so although I said that we're not going to be referring to where one is stabilized in the moduli space of cycle sizes, this mechanism for finding exponentially small vacuum energy does prefer a particular point or set of points in the moduli space. And if you go to those points, then it's quite clear what the axion properties look like. And they are actually a little different from the ones that I'll be describing to you today. If I was convinced that the particular constructions that are shown on screen now were just one step away from solving the actual CC problem, which is not what I'm saying. If I were convinced of that, then it would sort of behoove me to immediately go there and study axion properties there. The thing is, these supersymmetric ADS vacua with small cc are, I think, a very exciting toy model that opens a new perspective on the CC problem. But we're not yet talking about building realistic standard models in them. And the reason is the supersymmetry breaking scale in these models is Hubble. And so the Gravitino-Compton wavelength is Hubble. And so there's just no fixing that right now. And so it doesn't make yet much sense for us to talk about the properties of semi-realistic axions. You can't have a semi-realistic standard model in these vacua yet. Of course, we're trying to remedy that, but that's where we stand.
Okay, thanks. So is a rough summary that things might be different in whatever thing actually solves the CC problem, but we don't know yet. So this analysis is what we can do.
Absolutely. They very well might be different in the thing that actually solves it. If the thing that actually solves the CC is just a non-supersymmetric version of the SUSY thing shown on screen, then they definitely will be different in a way that I understand and can summarize to you at the end. When I've shown the whole story for sort of general points in moduli space, yes, we know how the pattern of moduli of axion couplings changes. Yeah.
Okay, thanks.
Great. Okay, thanks for that. So I'll close that parenthesis and we'll leave behind the ADS vacua for now and just talk about the Axiverse. So plan. First, I'll talk about how we build an Axiverse. I'll say a little bit about some of its properties, but mostly I'll leave its properties open for questions. So you can just ask me what you want to know about the distributions of the various observables. But mostly toward the end, I'll talk about solving strong CT in this Axiverse. Okay, so first the construction. Right, so let's remember what we have to do here. We're trying to solve string theory. The low energy effective theory in 10 dimensions is gravity plus other fields. And so the vacuum equations of motion are the Einstein equations. The vacuum Einstein equations in 10 dimensions for a product ansatz, like a 4-dimensional space times a 6-dimensional space, break up into the 3+1 dimensional Einstein equations in vacuum and the internal 6-dimensional Euclidean Einstein equations. So our mu nu equals 0 and our mn equals 0. Well, if we study Minkowski space times an internal space, then the our mu nu part equals 0 is automatically fulfilled. But what we're left having to do to find a solution of string theory is find a compact 6-manifold that has vanishing Ricci tensor. So Ricci flat 6-manifold. That's what we'd like to find. So a vacuum solution of string theory, a solution of string theory in the absence of any sources of stress energy is a compact Ricci flat 6-manifold. Because how do we find these things? Well, the Einstein equation is some PDE, so you could just imagine solving it, but it's a really hard PDE, and it's only recently been solved by Shamit and Max and Arnav, in fact, for 4 real dimensions, so K3, not 6. 6 is still out of reach. And what does everybody do? What all string theorists have been doing on this front since about 1985 is using Yau's proof of the Calabi conjecture. Okay, and the Yau proof of the Calabi conjecture guarantees that there exists a Ricci flat metric if you fulfill certain topological criteria. And the space is then called the Calabi-Yau threefold. So this presents an easier game. Rather than having to try to solve PDEs en masse, what we can try and do is find spaces that fulfill these topological criteria. Okay, so that's the game. Now, many Calabi-Yau threefolds are cut out as hypersurfaces, complex codimension 1 hypersurfaces, in simpler spaces called toric varieties. You can imagine you have some simple, relatively regular toric variety, and you cut out a nice curved Calabi-Yau threefold out of it. So what's a toric variety? A toric variety is a complex manifold that you can make by gluing together copies of algebraic tori. An algebraic torus is just the complex plane subtract the origin. So it's the punctured complex plane. And so a toric variety is a manifold that you make by gluing together a whole bunch of punctured planes according to some instructions. Instructions that are encoded in a polytope. And so a polytope is just the general dimensional generalization of a polygon or polyhedron. And so what you should picture is you have some polytope that gives you a recipe for how to glue together punctured planes in a way that makes an interesting space. So here's my favorite example, CP1 complex projective space, which is topologically a two-sphere, can be made as following. Take the punctured plane, add a point, namely fill back in the puncture, and then add the point at infinity. Now you've made the Riemann sphere, which is a two-sphere. Okay, so all of the constructions we'll be thinking about are just much more elaborate versions of this same kind of business. So there's a vast class of toric varieties that are encoded in four-dimensional polytopes, and those polytopes have been classified by Kreutzer and Skarka, and there's 473,800,776 of them. So just to give a bit of a sense, if you try and do this in 2 dimensions, there's only 16, here they are, and then one just has to picture a slightly more complicated set of objects in 4 dimensions. Okay, so this is our raw material that we're going to use to make an Axiverse. So the starting point is this set of 473 million polytopes. But to compute the topological data of the Ritchie flat 6 manifold, the Calabi-Yau threefold, what you need to do is triangulate the polytopes. And to triangulate a polytope just means to break it up into simplices. So in this case, triangles. And there's 2 ways to do it in the case of a square. But you can picture if a polytope has a lot of different faces, there's going to be a lot of different ways, in fact, combinatorially large number of ways of breaking it up into simplices. And that's what makes the problem complicated. On the other hand, combinatorial things are pretty easy to automate. And this gives us a combinatorial access point to Vacuoah of string theory, and that's really what we've been making use of. So you can think about the following hierarchy of automation. It's pretty hard to solve PDEs anyway, and it's really hard to solve them in large ensembles in a reliable way. What people have traditionally done is say, forget about solving PDEs, I want to solve polynomial equations over the complex numbers. That takes you to the realm of algebraic geometry. But that is a complicated and ancient art, and it's hard to learn and it's hard to really use. Even the great practitioners have a hard time doing the computations we need to do in the algebraic geometry realm. In fact, even the greatest ones usually can't do those computations in the realm of polynomial manipulations. And so something that makes it still yet easier is if you transform a problem of algebraic geometry, a problem of polynomials, to a problem of combinatorics. So just trying to find integers that fulfill certain constraints. That's great, that's a lot easier. It's not easy per se. So the number of triangulations that show up in the Axiverse we're looking at looks like the following. So what you see in this plot, H11 is n, the number of 4 cycles. We'll come back to that a lot. So it's the number of axions. The largest possible number in this set is 491. And the one that I've circled up there has about 10 to the 928 triangulations. It's given by that binomial coefficient. Strictly speaking, that's an upper bound on the number of triangulations that we proved, but it could be close to that. That's not the number of distinct Calabi-Yau threefold geometries. The number of distinct Calabi-Yau threefold geometries is a factor of 10 to the 500 smaller, but that's still 10 to the 428. So there's still a stupefying number of possible Calabi-Yaus there. Okay, so we have to somehow wade through this complicated space. So this is where our machinery CY tools comes in, purpose-built to analyze these kinds of triangulations that can do it an awful lot faster than any of the other codes that you might be able to get. And that opens up this big realm. You got a lot of polytopes, but then a truly great number of geometries. And this is now still just for context about where things stand. Let me show you a little bit about what we've been able to learn how to compute. So here the axes are the number of 4 cycles in the x-axis and the number of 3 cycles in the y-axis. Each point is a collection of Calabi-Yau manifolds that have that number of 4 cycles and 3 cycles. And as the number of cycles increases, the complexity of the computation grows exponentially, at least naively. And we'd like to get out to the circled one, to 491 or something like that. We'd like to understand the big spaces. So when we got into this in 2014, that pinkish purple band was the only part that anybody could analyze even on a computer. And so that needed to be fixed, and we fixed it. Now we can just analyze the whole thing. We can run through the whole realm. It used to take hours to study even one, and now it takes milliseconds to compute triangulations and maybe seconds to compute all the data that you need for one geometry. So, and this is on a laptop. So that's great. Now we can easily ask and answer the questions we want, and let's try and get some physics out of this. So we generated millions of hypersurfaces, And we claim they're an unbiased sample of the possible topologies. So the distinct polytopes, distinct triangulations are sampled with equal probability. But the trouble is for each topology, there's a moduli space of geometries. There's a manifold worth of geometries. Because if you're told the topology, you still have to ask, well, how big are the various cycles? And for us, it'll turn out the sizes of the 2-dimensional, 4-dimensional, and 6 cycles matter the most. And so we've got to figure out what sizes shall we assign to these things. So this number H11 that keeps coming up, which I'll be calling N, counts the number of 4 cycles. So it's the dimension of the this homology group of the Calabi-Yau threefold. Now, as I implied earlier, and as you may know, there are 2 fundamental expansions in string theory: the genus expansion that's analogous to the H-bar expansion, and then the alpha prime expansion, or curvature expansion. And for the curvature expansion, the coupling parameter is, roughly speaking, the string length squared times a curvature of the target space, so like our spacetime, or of the internal space.
Liam.
Yes.
Sorry, a quick question.
Yes,
So
please.
This has come up, and you've given the number 491 a few times, and as
Yeah.
I understand it, there's several of us here, so we have to. As I understand it, this is just a computational limitation. 491 is the highest you could go.
No.
Okay.
No, 400. Yeah, thanks for asking. 491 is the largest anybody has ever found.
Okay.
And there are open conjectures, not, I think, profoundly well-motivated conjectures, but sort of reasonable conjectures that say that this is the farthest you'll ever get. For example, it's known, if you know what an elliptic fibration is, it means you can put a 2-torus fibration inside the space in a certain way. You can prove that 491 is the largest H11 that will ever arise in an elliptically fibered Calabi-Yau. Now, have we found all the Calabi-Yaus? No, we don't know that. But in this Kreutzer-Skarka list, okay, 473 million polytopes, you can just list all the H11s, and they go up to this number, and there they stop. Now, if we wanted to analyze a case with H11 100,000, we could actually. It would be slightly slow on a laptop, but we could do that. Nobody actually knows why it stops there. There have been attempts to prove consistency conditions, bootstrap style consistency conditions or something, but that has not been settled. So I don't think anyone can give you a good answer of why it's not 492 or not 600.
So within this, within my list, I can start at, I don't know, 1 or 2, and I can go up to 491. Is there some well understood sense of which numbers there are most likely, which ones are least likely? Maybe you said this and I missed it.
No, let me see if I can get the image to come back up. It's something odd about the slide that it's not showing up. Okay, so here's one thing. Yeah, this is the measure problem. Okay, so you might say, should I count these things by each different topological type as one distinct thing? Well, if you're going to do that, the number of potentially distinct threefolds appears to grow exponentially with H11. It turns out that the number of, the upper bound on the number of distinct threefolds with H11 equals 491 is like 10 to the 20 bigger than all the other ones put together. Now, I can't make a sharp statement about that because I can't prove that the upper bounds are nearly saturated. So it could be the case that most Calabi-Yau threefolds have H11 equals 40 or something like that. But there are pretty decent signs that most of the complexity is up at really large H11. Look how high the rightmost dot is above the second to the right dot. But we just don't know if that's the right way of weighting things. Maybe you should weight things by how many distinct polytopes have that Hodge number, and that peaks at 30. So H11 equals 30 is where there's a few million polytopes with H11 equals 30. At H11 equals 491, there's just one polytope, but it's got up to 10 to the 928 triangulations. And so, these are some sort of competing speculations, and we just have no idea which one ought to dominate. And so what we're doing is a sort of a conservative first pass is weight different topologies equally, and then see what we can make of it, and then try and reweight things later on. But yeah, that's a really actually important question about this line of work that we aim to do better on, but so far it's completely murky where most of the distinct threefolds even are.
Thank you.
Yeah, thanks for asking. Other questions now? Okay, so we got to figure out how big the various cycles are, and we can compute efficiently, we understand what we're doing when the string coupling is small, which will be the case all the way through, and when the curvature is small in string units. So you want the space to be ample in size compared to the string length. Okay, so you have some big space and small strings, then you're in good shape. So it's going to suffice if all the cycles are large in units of the string length. That's actually not necessary. For the experts, there are some 2 cycles that you can shrink down to 0 size and not have any trouble, but that would be a whole talk. And happily for us, our results will either way. So we're not going to need to deal with that. We'll just take all the cycles to be decent sized in units of the string length. So you can picture a nice supergravity approximation. So let's see how to actually do that. The number of 4 cycles is counted by n, each one, particular Hodge number. And so if there's n different 4 cycles, then the moduli space of 4 cycle sizes is some subset of R to the n, because I have to tell you a real number for each cycle. And in fact, it's a cone, the Kähler cone in R to the n, pictured here. And it's a fact that on the walls of the cone, 1 or more of the cycles have shrunk down to 0 size, but inside the cone, all the holomorphic 2 cycles have positive size. So this is the region in the space where the supergravity approximation is good, where the curvature of the space is small. And once you land on the wall, coming from the inside and reaching out to a wall, you're facing potentially large curvatures. And outside this cone, no good. Okay, so this is the arena we can work in. And we're going to define the stretched Kähler cone, K tilde, to be the subcone of the Kähler cone where not just the case that all the 2 cycles have positive volume, but I want them to have volume at least 1. So here's a diagram of that. So here's a picture of a Kähler cone in 2 dimensions, the generators of these 2 rays. And on each of these rays, a different 2 cycle has 0 volume. And in between the rays, those 2 cycles both have positive volume. And the stretched Kähler cone is the checked region inside. And the red arrows tell you, you got to stay away from the walls if you don't want things to be shrunk down to 0 size. And so it's actually inside the stretched Kähler cone that the alpha prime in expansion is controlled. It's inside the stretched Kähler cone that the quantum gravity EFT makes sense and we can compute it. That's where we'll be living. Questions about the Kähler cone and the stretched Kähler cone? Okay, now here's a key observation, which just comes from Euclidean geometry. Suppose you got some narrow cone with many walls. It doesn't have to be a Kähler cone or anything, just some narrow cone with a lot of walls. Then the subcone, that's distance at least 1 from every one of the walls, has its apex far from the origin. Okay, so now, there's a fact, which we've pulled out from some analysis. When n is large, so when you've got many axions, the Kähler cones are indeed narrow and have many walls. So by the above proposition, stretched Kähler cones have their apex far from the origin. That looks like this. The upper of these 2 figures is a not super narrow cone, and the blue arrow shows you that the apex of the stretched cone is pretty close to the origin. In the lower figure, it's a quite narrow cone, and the longer blue arrow says the apex of the stretched Kähler cone has gotten a lot farther from the origin. Now, this is what I've shown you in 2 dimensions. You should picture this happening in 200 dimensions where the effect is much, much more dramatic because there's so many more walls to deal with. But the fact that the apex of the stretched Kähler cone is far from the origin is the driver of the main result I'll be talking about. The region we're sampling, the region where the supergravity expansion makes any sense, is a region in which some cycles are really big. That's what it means to be far from the apex. It means things are large. And how big? Well, some power of n, we'll see. But other cycles have volumes of order unity. And that means we see hierarchies of cycle sizes by powers of n. We have some cycles of order 1, of order n to the 4th, etc. And this is the main finding: topologically complex compactifications are anisotropic. So you can illustrate it. It doesn't require actually a Calabi-Yau and a Kähler cone to describe this. Consider a spherical cow of radius r cow. And question, let's find the minimum radius of the cow such that all of the spots on the cow have size at least 1 meter. Okay. Well, first answer, let's say we assume a isotropic spherical cow. Then the radius of a spot is about the same as the radius of the cow. And so the minimum radius you need is going to be about 1 meter. So it'll suffice to make the cow 1 meter. But the more detailed answer is, well, wait a minute, if you have an anisotropic cow that has many spots of widely varying sizes, you're going to need to make the cow large overall for its smallest spot to be at least a meter in size. And that's essentially all that's happening here. The Calabi-Yaus that we're dealing with have many, many cycles, and their cycle sizes, the cycle sizes are different necessarily. And if you want to make the smallest of them at least one, then the biggest ones get truly large. Okay, so this is the main finding. Any questions about that?
Sorry, can you remind me what's wrong when you get to the close to the wall of the cone?
Yeah. When you get close to the wall, some of the cycles are getting small in string units, and that means that there are uncontrolled expansions. So as an example, shrink some cycle down, and you can have strings wrapping around the region around that cycle. If the cycle is contracted to be much smaller than a string, then you can't easily neglect excitations of the string for the purpose of computing the effective theory. Okay, in very technical terms, the curvature expansion has contributions from worldsheet instantons, which are string worldsheets that come and wrap the cycles. If the cycle sizes are small, then the worldsheet instanton actions are smaller than 1, and you have what looks like what should have been a series in e to the minus a large action, and it's a series in e to the minus a small number, and so the series diverges. And so you have uncontrolled corrections to the effective theory. Now, it doesn't mean that quantum gravity doesn't make sense there, but it means that one doesn't have a weakly coupled quantum gravity theory. And so we're out of luck as theorists trying to understand those regions.
Okay, thank you.
So in case that wasn't clear, in this region, this white region between
here.
Well, you can finish.
Oh, sorry. It's hard to coordinate. Yeah, I guess you can finish and then we'll ask a question. Sorry.
Yeah, was there another question? Please go ahead.
Oh yeah, sorry. I think I might have just missed it. So what is the reason outside of the Kähler cone you cannot? This is bad. I'm sorry.
Yeah. Outside of the Kähler cone, it depends on how we want to talk about it. Typically, what happens when you get to the wall of the Kähler cone is some cycle shrinks down to 0 size, and when you go to the other side of that wall, the cycle re-emerges at finite size, but in a different Calabi-Yau. And so, in fact, if you can remember the sort of trippy picture of tons of different colored polygons that I showed at the beginning, each of those little polygons was one Kähler cone region. And if you go from one to another, you're going through a wall to a new Calabi-Yau.
So it's not that you don't have control. It's just for the sake of classification, you want to just restrict yourself to one Calabi-Yau, or sorry, to one Kähler cone.
Yeah, that's a great question. So really what we're facing is some picture like this. Let me draw a couple of them at a time. Suppose we have regions A, B, C, and D. And inside regions A, B, C, and D, I can color in blue the corresponding stretched regions. Now, what you might first say is, why don't I just study inside the stretch regions, because then I definitely know what's going on. But wait a minute, what about these regions in between colored in red? That's sort of, maybe you're missing a lot of interesting stuff there. And a finding, a highly non-trivial finding, which took us a year to work through, is that actually you can understand these red regions pretty well. But if you sample them, the conclusions that we're going to quote at the end for things like CP are actually strengthened, not weakened. And so for simplicity, we're just going to look in these little blue patches. But then, for those who have the appetite, we're going to have a series of papers sorting out the whole stupid thing. But basically what we're doing is we found a lamppost that's simple, where the conclusions are already strong enough. And if you go away from the lamppost, in fact, the conclusions get stronger.
Okay.
So that's a fortunate thing. But if you'd asked me this question 3 years ago, I would have told you I have no idea what's happening in the red regions.
Okay, thank you.
Other questions at this point?
So it seems like you have this space of possible 4 cycles, and then it's restricted by enforcing that the 2 cycles are positive.
Yeah.
Like the 6 cycles or any of the other cycles.
Yeah, good. Right, so we've got 2, 4, and 6. It turns out that if you impose that all of the 2 cycles have decent volume, have non-zero volume, then also the other cycles will have, the 4 and 6 cycles will have non-zero volume. However, if you insist that all the 2 cycles have volume at least 1, that doesn't guarantee that all the 4 cycles have volume at least 1. So we'll have to impose that separately, and we will do so.
Okay.
The 6th cycle always comes out with large volume, very large, in fact. Okay, so right, so we have basic finding that you need to take the space to be quite big to be in the regime indicated by these blue regions where things are under a little bit of control. And so here, let me start to show you some pictures of results. Okay, so here's the scaling of the volume of the Calabi-Yau threefold. So vertical axis is the log base 10 of the volume of the 6th cycle, so the whole thing, versus n. And you see it grows pretty rapidly with n. In fact, it goes like n to the 5th. Okay, so the space gets pretty big. I'll skip over the KK scale estimate. You can look at the size of the smallest 4 cycle there too. Okay, again, log of the size of 4 cycles versus log of n. And you see there's a pretty decent fit to n to the 4th. So the 4 cycles go like n to the 4th. The exact numbers don't matter. What I want you to take away is that the cycles grow polynomially in n. And then this distance that I was quoting, so the length of that blue vector up at the top left, that's what's plotted here, log 10 of the distance in the vertical axis. And that turns out to scale like n cubed. Again, doesn't matter exactly how it scales, it's just that it scales up. Okay. So that's the construction. Now, I'll flash a few slides about some physical properties of the Axiverse, but then I'll turn to talking about CP. Okay. So how do we actually get axions here? In a 5-dimensional picture, if you imagine compactifying 5-dimensional Einstein-Maxwell theory on Minkowski space times a circle of radius r, that's indicated in the top line. If you dimensionally reduce the Maxwell term, one quantity that you can pick out as theta, which is the integral of the internal component of the gauge field along the circle. So that's an axion field, and the 5-dimensional gauge symmetry protects the axion potential. The 4-dimensional action that you get by dimensionally reducing this 5D action looks like some d theta with an axion decay constant that scales like 1 over the radius of the circle. And then, okay, here's the point that's quite important. If your 5D theory has charged particles with some charge q and some mass m, then if a particle has a Euclidean world line that winds around the compact circle n times, that gives a 4-dimensional potential that's an exponential of r, the radius, times n, the number of windings, times n, the mass, times some cosine of theta. Okay, so this is a relatively concrete 5D model. And I wanted to state it because in string theory, it's exactly the same thing, but with more extra dimensions. Okay, so I've just shrunk down that slide, and then here's the modified version of that slide. Now, instead of a circle, you have a Calabi-Yau threefold. Instead of a 2-form field strength, the Maxwell field strength, you have a 5-form field strength. Instead of the integral of a 1-form, you have the integral of a 4-form. You're not integrating over a circle, you're integrating over a 4 cycle. But otherwise, it's the same. And now it's not charged particles anymore, but charged D-branes, D3 branes, it turns out. And a D3 brane whose Euclidean world volume winds around some 4-dimensional cycle will give a potential that's exponential in the cycle volume. So exactly analogous to the exponential in the circle volume. Okay. So this is where the axions come from in the setting we're looking at. And so in the particular construction here, the Kreutzer-Skarka Axiverse, we're going to define N-axions, theta I, to be the integral of a 4-form potential C4 over any of the n members of a basis of 4 cycles. So sigma I for I equals 1 up to n are a basis of 4 cycles. So integrates the 4-form potential over those and you get the axions. Then you can work out what the axion Lagrangian is. It has some kinetic term. And then it has some potential term that involves exponentials of volumes of various cycles. Now, what are these objects? Kij is a constant n by n matrix whose eigenvalues are the axion decay constants squared. The object Q is a matrix of integers. It's just the expansion coefficient of some particular cycle in terms of a basis, which you can think of as keeping track of the charge of the 8th instanton under the ith shift symmetry. Now, I'm not necessarily expecting that everyone's happy with all the details here. It's maybe a little fast if you don't study these kinds of compactifications, but the point is we're working in a weakly coupled UV completion, and we can just compute all of the data that show up here. So the work is going to consist of computing n, the number of axions, the matrix Q of axion charges, the matrix K of axion decay constants, and then the volumes of the various cycles. So that's what we have to actually do, and then we know all the data of the EFT that we care about. Right, and remember what we're trying to do is track powers of n in the EFT. So just some pictures, some plots, what we get after looking at this for a while. Here's log base 10 of the axion decay constant in GeV, and the color coding tells you what H11 is, what n is. So the yellow stuff further to the right is geometries with n not very large. Then as n gets bigger, the curve shifts off to the left, and you see f ending up in a range that's really quite relevant for astrophysical experiments. And the axion masses, we'll come back to these things in a little bit. The axion masses similarly are plotted here on log base 10 of the mass in electron volts. Again, the color scale yellow is small n and blue is large n. And you see that there's a pretty sizable peak, but then a tail that runs off to super small values. And the pink bands are the bounds from black hole superradiance. The right one of those is stellar mass, and the left one is supermassive black holes. Now, let me, in the remaining minutes, tell you about what I think is the coolest outcome of all of this, which is a solution of the strong CP problem, and some work with Mehmet Demirtas, Naomi Gendler, Cody Long, and Jakob Moritz, which we expect will be coming out in the next couple of weeks. Okay, so strong CP problem just famously is the observation that QCD can have a theta parameter, and why is that theta parameter so small? So if you redefine the quark masses to make them real, the theta parameter shifts like this, then you can define theta bar to be theta minus the shift that you get from making the quark masses real. And the question is, why is theta bar less than 10 to the minus 10, as neutron EDM experiments will tell you. Peccei-Quinn mechanism famously promotes theta to a dynamical field, and QCD instantons give you a potential for theta, which has its minimum at 0. So at the minimum of this potential, CP is preserved. And if this were the only term, the strong CP problem would be solved. That's why this was such an important idea. Okay, but it's not the only term. And the problem, the quality problem in the Peccei-Quinn mechanism is that high scale physics, even Planck-scale physics, can easily break the PQ symmetry badly enough to ruin the mechanism and lead to neutron EDMs larger than those that are seen. So let's imagine there's some other term that breaks the PQ shift symmetry, some V breaking, which is some scale to the 4th cosine of theta bar plus psi, where psi is a number that's not 0 or pi. Okay. Well, theta bar is going to be in the observably allowed range only if this coefficient lambda to the 4th is less than about 10 to the minus 14 GeV to the 4th. And that's a pretty stringent constraint. One way that you've presumably seen this written, you can write some field capital phi, which has as its real part f and then e to the I theta. And you could just try writing down operators that are powers of phi and ask how constrained are the coefficients of these operators. And the bound, you just plug in these numbers, you easily see that even an operator of dimension 10, Planck suppressed, could kill you if f is 10 to the 10 GeV. So this is a well-known fact in some circles, but for a string theorist, this is particularly compelling, right? We love finding problems that are sensitive to Planck-scale physics because that's an opportunity for us to do something useful and compute in a Planck-scale theory things like which operators arise and what are their coefficients, right? So that's exciting. So let's just do that. Let's compute the Planck-suppressed corrections in this UV conclusion. So you can rewrite this bound, lambda to the 4th less than 10 to the minus 14 GeV to the 4th. You can just rewrite it in terms of instanton actions. Just define lambda to the 4th to be m Planck to the 4th e to the minus s, with s some number. And the bound means, it turns out that s is at least 200. Okay, so the statement of the PQ quality problem then is that every instanton carrying charge under the Peccei-Quinn symmetry must have action at least 200. Okay, so if every instanton has to have action at least 200, let's see, what does it mean? What's every instanton mean? Well, the only objects carrying charge under the gauge field C4 are D-branes. And so we actually know all the instantons that carry PQ charge. They're all so-called Euclidean D3 branes, so we can list them. We can enumerate all the leading instantons. This is the formula I showed before, that the potential for the axion is some exponential of volumes of cycle sizes. But the string theory input comes in saying, well, which 4 cycles actually support instantons? And how large are those cycles? That's going to determine whether the quality problem is alleviated or worsened or what. Now, the first question, which cycles support instantons, is a topological question. You just have to count how many fermion zero nodes are there. So that's a little technical, but one can do it. And question 2, well, the volumes of the cycles are just given by the expansion coefficients of a basis times the volume of the basis cycles. So if you know where you are in moduli space, you know how big the basis cycles are. And so you can figure out how big all the cycles are. So these questions are both answerable. That means we can determine, is it the case that every instanton carrying PQ charge has action at least 200? But there's a simpler point here, which is that all the actions are proportional to 4 cycle volumes. So you can trivially make the Calabi-Yau large enough so that all of the actions are bigger than 200. Just take the space, whatever it was, and dilate it uniformly. Dilate it uniformly until the smallest 4 cycle is volume at least 200. That's no good. That's not a solution to the PQ quality problem because the gauge couplings get small in the same limit. If you're engineering the standard model on, let's say, T7 branes wrapping a 4 cycle, then the volume of that 4 cycle governs 1 over the Yang-Mills coupling squared. So if you try and dilate the space too much, every gauge theory is going to be really weakly coupled, and that's not interesting anymore. So what we really want to know is, can we have all of the actions bigger than 200 while keeping the correct standard model couplings? Now with TeV scale SUSY breaking, the standard model couplings turn out to correspond to the 4 cycle that supports QCD should have volume 25. If you change the scale of SUSY breaking from TeV up to the string scale, or decay scale, this volume changes a bit from 25 up to about 40, but our conclusions actually get even stronger. So I'll just work with 25 as a reference point. So what we're going to do then is we're going to consider every distinct Calabi-Yau threefold in our ensemble, find every 4 cycle that could support QCD, adjust the size of that cycle until its volume is 25, and that gives you a UV completion of gravity and QCD. Okay, that's the PQ Axiverse. And in this model, we want to compute the actions of all the other instantons. And if all the other instantons have action bigger than 200, the PQ quality problem is absent, and the Peccei-Quinn mechanism solves the strong CP problem. If any of the other instantons, if a problematic instanton has action less than 200, then the quality problem is not alleviated. Okay, so so let's see if there are questions about this, and then I'll actually show you the results, and then I'll conclude. Questions about the strategy for addressing the quality problem, or understanding the degree of the quality problem.
Just one question here. So you're talking about that you have a manifold that you can have a QCD and the axion thing. Do you care about having the rest of the standard model there as well, or not?
Yeah, right, good. We do, but it's not going to be particularly constraining to do that. What we don't have the ability to do right now is engineer the whole standard model, get all the couplings right, and make sure that there's no vector-like matter. We probably will acquire that capability in the next couple of years, but especially the figuring out whether there's extra vector-like matter is a brutal problem that's vexed people working on string compactifications for a long time. So we are not building perfect visible sectors here. But what I don't think will change is if you go from the ensemble that I'm describing, where we just have some toy model of QCD, and you decorate it to make it a real standard model, that won't change really where you need to be in the moduli space, and it won't change, I claim, the solution of the strong CP problem. So bottom line, I do care, but for the purpose of solving strong CP, it won't matter.
Okay, thanks.
Thanks. Other questions?
So you flashed up a couple of these slides, like the distribution of decay constants, the distribution of masses, a little while ago, and now we're talking about QCD axion.
Yeah.
The QCD axion would not have been included in these guys, right? Because the QCD axion is not one of these, integrals of this four form, right?
Yeah. Thanks for asking. It is one of them. It is one of them. So if I specify that a particular four cycle has D7 branes on it that support QCD, then we can think of the integral of the four form over that four cycle as being the QCD axion.
I see. Okay.
Now, what I haven't done here when showing you the masses is I haven't carefully incorporated low energy QCD effects. So one of these axions, if I have N axions in my histogram here, one of them probably should be adjusted a little bit to incorporate, some lambda QCD to the fourth type things.
Good. So that one, let's say you're looking at your histogram here and you see that one guy that ends up being a QCD axion.
Yeah.
Is his potential is actually going to be dominated by something completely different. It'll be the QCD instanton effects. And so even though all the other guys may be down at 10 to the negative 10 EV, for all you know, the QCD axion is somewhere completely like that is not necessarily tied to this histogram. Is that the impression I should get?
Well, yeah. So that's a great question. We don't. I know now, but we didn't know when we started the calculation, and I'll tell you in a moment. Because whether the QCD axion has a mass very different from all these other things is sort of is the question of the quality problem. Because if high scale stringy instantons give masses to the QCD axion that are order, I don't know, kilo electron volts or something like that, then certainly quality is spoiled.
Right.
And so the question is whether when you include all the stringy contributions to the QCD axion potential, is there a really light direction left? We'll find that the answer is yes. That's why I'm saying the quality problem is solved. So, when we were finally done with the computation, we looked and said, oh, good, yes, it looks like, in fact, the QCD axion, its mass is dominated by low energy QCD effects, but that was not something you could guarantee, by symmetry or by decoupling or something like that. In fact, the PQ quality problem is the statement that you can't guarantee that by decoupling. You have to instead compute in the high scale theory and ensure that you're okay.
Sure. So maybe I can ask a slightly different version of the question I just asked, which is in histograms. I should think of these histograms as plotting the results from all the like a bunch of string instantons.
Yeah.
The instantons that are giving rise to the QCD potential are completely separate. Like that's really that's not arising from the same effect. I mean, that is what you're going to say at the end when you say that the quality problem is the quality problem. That amounts to the statement that really the instantons that are dominating QCD's axions action are not the same as the ones that are being shown in this histogram.
Correct. Not only are they not the same, but also the low energy QCD instantons are strictly more important than these stringy ones, right? And so that certainly wasn't a guaranteed thing from the beginning, because if there was just one cycle with size of order 10, then there would be an instanton with action of order 2 pi times 10, which is a heck of a lot less than 200, and you would be completely crushed and the QCD axion would get some big mass. Now, we do find actually that there's some subset of our examples, I'll show it in a moment, where the QCD axion does get a big mass from stringy instantons, and quality is spoiled. But all of those things occur when n, the number of axions, is less than about 15. And once n is big enough, the QCD axion is free.
Thank you.
So I have one more
Yes,
question. Maybe you'll tell us, but do you have examples where, say, the QCD axion does not get a large mass, but you still have string instantons that are comparable? Like, for example, they simply don't couple in a way that destroys PQ.
Yeah, absolutely. That's definitely a possibility. It's not a super common possibility. I don't have a histogram to show you how uncommon it is, but what we really checked was the following thing. So if you've picked out a cycle that supports the 7 branes that host QCD, then you have a particular direction in your charge lattice, your n-dimensional charge lattice Z to the n, that is the QCD, that is the direction for QCD itself. And what one tries to do is ask, let's find all of the instanton effects, all the stringy instantons, and order them from the most important to the least, and start with the most important one and ask, does that go along the QCD direction? If it doesn't, put it in and take the next one and ask, is the QCD direction in the span of those first two? And go on and on. And when you finally get to the end and you're like, okay, I've included all of these things down to action bigger than 200, and there's nobody contains the QCD direction, then you say, okay, cool, quality is not spoiled.
Okay.
If on the other hand, at some stage in that process, you put in an instanton and you say, oh, this one now the span of these instantons I have so far included does contain QCD, then you say, aha, quality is spoiled. The quality spoiling effect has action, S, whatever number less than 200 is you're dealing with, and then the QCD axion mass from stringy instantons. And so your question was, can it happen that that there are plenty of instantons with actions that are important, but they just don't go in the QCD direction? And yes, that can happen. But crucially, we're not mostly living off of that. We're mostly living off of the fact that most of the actions are pretty big.
Okay, thank you.
Okay, so right, so we need to understand how big are all these various things, and there's the result. So what I'm showing here is delta theta stringy on the vertical axis, number of axions on the horizontal axis. The gray band is excluded because theta bar is bigger than 10 to the minus 10, and below that line it's allowed. And note the tick marks. The tick mark below 10 to the minus 10 is 10 to the minus 1,000, then 10 to the minus 10,000, et cetera. So most of these points are at completely absurdly small levels of theta bar. Okay, so theta, when I say delta theta stringy, I mean the contribution from Planck-scale physics to theta. So when you're down in that region, in the white region where it's allowed, it just doesn't matter what the stringy contribution is, because the QCD, low energy QCD instantons set your minimum at 0 and you just sit at 0. So only in a really thin band right below 10 to the minus 10 could you possibly see EDMs in some future experiment. Now, a previous question was, what about, can the QCD axion ever get some mass? Actually, these dots up at the top in the excluded region, those a bunch of big dots up there, those correspond to cases where the QCD axion gets such a big mass from quality spoiling effects that you're completely excluded, but also the QCD axion evades the astrophysical and cosmological bounds because it's just so massive. It gets to 10 GeV or something like that, and you're not worried about stellar emission or overclosure or anything. Okay, now what I guess I should do is go through a couple of statements about astrophysical and cosmological constraints on this same setting, and that will allow me to explain what are the different dots. Why are some of the dots different shades of gray? I'll bring this plot into color. And what I'd like you to observe first, though, is that for n bigger than about 20, 15, depending on how you count it, quality is basically automatic. It's extremely hard to find a model with bad quality when n is bigger than about 20. Okay? And that's just coming from the basic scaling law. So delta theta is like e to the minus the volume of the smallest Four cycle. And I showed you before a plot pictured here in small inset on the right, in which I said the volume of the smallest Four cycle goes like n to the 4th. Really, it's 10 to the minus 2 times n to the 4th. And so when you work it out, you find that for n bigger than about 20, the smallest Four cycle has action bigger than 200, and so it just doesn't spoil quality. Okay, so some general qualitative lessons. Anisotropy of a complex space like this leads to large Four cycles, some small ones, and that leads to a small theta angle. And let me stress that we've enumerated all the potentially significant terms. There's no Planck slop left. There's no Planck suppressed operators left. For these weakly coupled UV completions of gravity, this is the final word. Now that could easily differ in other landscapes, but for this type 2B landscape, this is how it goes. But now, okay, a couple words on the astrophysical and cosmological bounds. Is it okay if I go for a couple minutes?
Yeah, that's no problem.
So we want to impose the axion dark matter is not too abundant, a standard bound there, and impose the standard bound on the coupling to of the axion coupling to two photons. We're not being very sophisticated about this yet. turns out a little bit non-trivial to properly impose these kinds of bounds for multi-axion landscapes with mixing, and we haven't done that super well. But the present estimates should be parametrically correct, and they might be off by factors of order 10 or so, perhaps a little worse in some special cases, but approximately there. So qualitative lessons, when n is large, some cycles get big. When cycles get big, f gets small, and that's bad for astro bounds. Because G sub A gamma gamma gets big. When n is large, you get large cycles, you get small f and small masses, and that's good for Cosmo bounds because mf to the fourth is small. And also large n gives you large cycles, gives you highly suppressed instanton effects because the instanton actions get big, and that's good for CP. And so let's see how these things play together. So first, the stellar emission bound, or anyway, the coupling to photons bound. You see the excluded and allowed regions above and below the line as a function of the number of axions. And now here I've colored in red the ones that are excluded by dark matter, and in green the ones that are allowed by dark matter. So the ones in green and below the line are allowed by dark matter and astrophysics. Similarly, we can write the dark matter abundance, omega axion over omega matter, as a function of the number of axions. And again, color code it whether it's allowed by the other bound, the stellar. Oops, sorry. The red allowed by stellar should say excluded by stellar. Although there's not many red dots, apparently, so it isn't a big deal, perhaps. And now I can put those things together and I can color code the plot I showed you already. So these are the same dots that I showed you when I talked about quality before, and this is the last slide before the conclusions. And now we can sort of take apart what's happening. The green dots are the dots that are allowed by the Cosmo and astro bounds that I described, and the red dots are excluded by one or the other or both. Now the little population of green dots up at the top where it says no light axions, there's no light axions, including the QCD axion. There's so much quality spoiling that the QCD axion is heavy. Okay, then you don't have to worry about QCD axion being emitted by stars or overclosing the universe. And that's why those things are allowed by Cosmo and astro. But the main population of green dots down at the bottom, which have absurdly small delta theta stringy, 10 to the minus 10 to the 5, those are allowed by everything that we know of on the Cosmo and astro side. And so what you see here is if the number of axions is bigger than about 20, then quality is automatic, and you have a decent chance of also fulfilling the cosmological and astrophysical bounds. Okay, and this wasn't, by the way, set up as a sort of a mechanism to try to solve PQ. We just wanted to ask how good is PQ quality in this landscape, and the answer is at large n it's really good automatically. Okay, so let me conclude. We constructed an incarnation of the string Axiverse. We found hierarchies of cycle sizes by powers of the number of axions n. And these hierarchies govern the actions of instantons that give the UV contribution to the breaking of the PQ shift symmetry. When n is bigger than about 20, the breaking is just negligible, and so the PQ mechanism solves the strong CP problem. And maybe PQ quality isn't such a problem in weakly coupled UV completions with many axions. Thanks a lot. And sorry for going over time.
That's fine. Well, thank you very much. There's quite a lot of questions throughout, so that's natural. Any other questions?
We have a couple here.
I have a quick question, Luke. So if we go back to the summary slide with the green and the red points, just this most recent one. Beautiful. Okay. So in the green points that are like for n, let's say greater than 30, have you guys also computed things like you're well allowed by the Cosmo bounds? I imagine that also means your fraction of dark matter that's occupied, like the total cumulative fraction of all axions in dark matter is most likely pretty small. Do you have, is there some kind of quantitative, roughly how much this is, or how does it depend on n, or things like this?
We don't have anything quantitative yet. You know, if you look at this yellow band there toward the top of the green region, that's where you're allowed by axion dark matter, but you know, maybe there's a little bit of fraction. And so just a little bit above this line, you're a little bit ruled out. So sort of the topmost green dots in that population are ones where the axion is an appreciable fraction of the dark matter. Now, you said cumulative, right? So the hierarchies here are such that we don't typically find that there's many axions contributing to the dark matter, because when you have a wide spread of cycle sizes, you've got a really wide spread on in the mass spectrum.
Sure.
And in MF to the fourth, it's not that common that you find more than one or two things in an interesting region. Typically, you find one, sometimes two. And so, yeah, it's typically the case that you have a pretty small population of dark matter when you're allowed. And if you go to the green dots lower down in there, it's a really negligible population.
Sure.
Just to ask at this point, for the dark matter, you're assuming order 1 misalignment? Is that the idea?
Yeah, so we were assuming order 1 misalignment, but not like on the hilltop. So
Okay,
order 1, but in the quadratic basin. Okay, and so you could have more trouble if you and what one could perhaps do, perhaps we should do this eventually, is sample uniformly from 0 to 2 pi and see how often you do land on a hilltop and get an extra boost. But we didn't do that yet.
So excluded here just means like if you take order 1 misalignment, it's possible for these things to be valid if you happen to be lucky.
Right. You could move the excluded bar by saying that there's some coincidence that makes all the misalignment small, or the misalignment could put you closer to the hilltop and you could move it the other way.
Or anthropics or whatever you want to.
Absolutely right. Yeah.
And can I ask, let's say I kept this plot going to the right. So I kept going up to 100 or 200 or 491.
Yeah.
How does this continue to scale? Like, it looks like this band is moving down. So is there some upper bound on the number of axions beyond which it's basically always ruled out by cosmology bounds?
Yeah, so this is, okay, so now here's the same data points, but on a log scale. So now the horizontal scale is log H11, and you can actually see sort of the power law behavior. If you ignore the green dot population on the top line, which is the ones where there's no light axion, you can see how this thing sort of trends downward. On the other hand, the green line is flat, the top of the green line. And roughly what's going on there is, okay, the delta theta stringy tending downward is just these overall power law scalings. And then you can try and figure out where is it that you're going to find the sort of marginal contribution to dark matter, and that lies on this relatively flat line at the top of the green region. Now, what will change, I'm pretty sure, although I don't have these plots for you right now to large H11, although we have some of the data, is the astro bounds. And the reason for that is if we go back for a minute to the distributions at the level of not histograms, but a level of curves, what you can see, like if you look at the dark blue lines, like up at 491, you see there's pretty substantial support at f less than 10 to the 8 GeV. And so you're eventually going to get killed by stellar emission type stuff.
Sure.
This deserves a careful analysis. We haven't yet been able to do that analysis. What I mean by haven't yet been able is we've been too busy finishing this other stuff. We have the computational tools to do that. And I think it'd be really fun to know how often is it in this really large N regime that you can manage to dodge having at least one of your axions that's emitted pretty substantially and violates the G sub A gamma gamma bounds. I think, I think it's going to start to hurt when H11 is bigger than like a couple hundred. I mean, 300 or something, you're probably in really big trouble.
And-
Sorry.
Oh,
Sorry.
Robert, go. I asked Robert.
No, so I was going to say, another thing, when you have many of them, is presumably that the chance of one of them lying in a super radiance type window becomes higher. But then it's a question of what the F is for that one as well, right?
Good. Okay, so for super radiance, there we have a paper on it.
Yeah.
And yeah, that was a question which we thought was sort of interesting to look into. And our basic finding is that typically you do find something in the super radiant window, usually about one thing in the super radiant window, in most of the range of N. And there are, however, two conditions that you need for super radiance, as many of you know very well, right? You need the mass in the right range, but you also need the F to be not so small that the axions are strongly self-interacting and they can destroy the condensate. And so, although as you keep on scaling up H11, scaling up N, you find greater and greater chances that you have axions in the superradiant band. Eventually the Fs start to go small enough that the condensates get disrupted. And so what we found is, if this is N up to 491, 1 and about 150, we plot the probability of exclusion by superradiance, by existing superradiant constraints. What we found was something that looked roughly like that. And the reason is, as you go up, you get more and more chances to have an axion lie in the superradiant band. But at a certain point, the Fs start to get small enough that you disrupt the formation of the condensate. Yeah, that's another constraint that where we think we know how that works, but what we haven't done carefully is the couplings to the standard model, like the astrophysical constraints in the large N regime.
But Liam, do you have like in these curves that you're showing, do you have are there like nice scaling laws for where the peaks of these curves go? Because there's very clearly a trend, right? As N goes up, F is decreasing, it looks like, right? And similarly with M. So
Like here?
Are there some kind of scaling laws for how the peaks of these curves depend on N?
Oh my gosh, I really wish there were. For years and years, I've thought that there should be some random matrix model description of this. Because after all, what are the Fs if not the eigenvalues of some large matrix? And we have an ensemble of those matrices. And surely we should be able to describe the change in the spectrum as some sort of 1 or 2 parameter family of random matrix models. Despite efforts that would have been sufficient in terms of effort outlay, but not in terms of results, to fill 3 or 4 papers over the last decade, I have never found a packaging of this that gives out a lot more than is put in. Like an efficient compression of the information that's in these curves. Now, part of it could be that we haven't been staring at the complete data for long enough. Part of it could be we just didn't try hard enough, but I don't see any like clean, obvious scaling laws in these quantities. We saw very clean scaling laws in things like sizes of cycles, right? Like this is, for the present purposes, okay, there's a lot of scatter, but this is a clear scaling law. I didn't find that for like, the minimum F or the mean F or something like that. You just get a lot more spread and a lot more diversity, and it's just not so clear that one can learn something from it. This is a source of continual frustration to me because it would be so nice and useful to have some simple sort of few parameter model, but I don't have one.
Sure. And one last question. I really appreciate all the patience.
Please keep on asking. Love it.
In these curves, is my understanding of how they're generated correct? So you pick, like, fix a number like 50 or 100 or whatever, and then go generate many different realizations of your specific set of cycles that correspond to this specific set of manifolds, specific set of polytopes, this, that, and the other. And then this curve is a sum over all that ensemble. Is that correct?
That's exactly right.
Okay.
Yeah.
So what is the variance of, if I just look at one guy, if I pick one guy that's N equals 50 and I were to plot his distribution of his 50 masses,
Yeah.
is it actually like gonna resemble this curve at all, or is the shape of this curve being dominated by the sort of ensemble effects rather than the individual?
Yeah, that's a great question. Okay, so for a fixed color in this thing, for a fixed H11, you have spread from the following thing. So you pick a polytope, and then you need to go to a triangulation of the polytope. Then when you have a triangulation of a polytope, that defines for you a Kähler cone, and inside that Kähler cone is a stretched Kähler cone. And what we were typically doing is sampling the region at the tip of the stretched Kähler cone. Okay, now you could do something different, which is you could sample other regions inside the stretched Kähler cone. But let's say you just do this. You pick a polytope, pick a triangulation, and for that triangulation, you get an effective theory. Now that's one effective theory. That one effective theory has some n by n matrix. So it has F1 up through Fn squared, right? It has n eigenvalues of the kinetic matrix. So N-axion decay constants. And okay, one indeed wants to know how much spread is there just in that eigenvalue spectrum. And then what if I took two different triangulations, how much spread? And what if I took two different polytopes, how much spread? In fact, what I really should have said is pick an n, then for that n, pick a polytope. For that polytope, pick a triangulation, and then look at the n eigenvalues, right? And the reason for this spread here is mostly this, just that the eigenvalues don't lie on top of each other. So most draws from the distribution at fixed n are roughly similar looking spectra. It's not that you march out over a much wider range as you vary the triangulation. You do vary somewhat. Okay, so also if I show you these ones, another way of viewing the scatter is the vertical line here, right? So fix some H11 and you see that what the volume of the 6 manifold is. Well, it goes from like 10 to 5 up to 10 to the 12 or something like that. That scatter is coming from the polytope choice and the triangulation choice. And now a great thing would be to combine these two most recent questions and say, are there scaling laws that sort of capture this spread or that spread or that spread separately? And there too, unfortunately, I don't have anything yet. It doesn't seem out of reach, but it would require some dedicated work to tease out those kind of patterns.
Sorry, I actually have a meeting with a student. Just joined my room,
Right.
so I gotta go. But thanks so much, Liam. You should.
Thanks, Peter. Bye-bye. Take care.
So is that question finished? Sorry, I had a related but slightly different one. So your sampling algorithm is that you sort of choose, if you're given n, you choose a thing randomly among, I can't quite remember exactly how you did it, but so randomly among the polytopes and then randomly among the triangulations or something like that.
Yeah.
Is there some dynamical reason to think that that's sort of how things might turn out? Or alternatively, are there sort of dynamical reasons to think that you might get some completely different measure?
Yeah. This now is related to the question of, what if we study the vacuum stabilization mechanism that leads to ADS vacua or something like that? That takes one to a rather different place. And that prefers certain kinds of polytopes. And for those polytopes, it prefers certain triangulations among them. What's really hard to say, it's one thing to say we have some sort of counting measure on a finite but large set, some large discrete set of different topologies, and we're weighting them equally. We'll sample them with equal probability. Once we get into the realm of dynamical measures, then one also has to weigh in sort of eternal inflation type measure factors. And then life gets pretty complicated. And so I haven't the slightest idea how to finish that undertaking once I start it. And so I've been trying to stay as far away from that deep water as I can. But that necessarily requires then making statements that are just statements of relative properties of distinct topological types without accounting for maybe some of those topological types are dynamically preferable. Now, one thing would be really fun is to understand the dynamics that changes this, right? Some dynamical process by which you move from one kind of topological type to another. Brian Greene and others have thought about this in the last 10 years or so. It's not something I think that we understand particularly well yet, but you could imagine sort of some wave function spreading over the space of triangulation and picking out something. But that's some years ahead.
Hey, thanks.
I think I just have one last question. So that's just in this picture you've drawn, you picked out the tip of the stretched Taylor cone, and you say, this is the sampling we're doing. If I move deep inside this, does everything, do all these effects just get smaller because I'm increasing some cycle size?
Absolutely, yeah. So now you go to here, you go from the blue star to the red star, you've dilated everything.
Yeah, okay.
And so all the actions get bigger by that factor. Suppose you dilate by a factor of 10. All the actions get a factor of 10 bigger, all the decay constants go down, all the masses go down exponentially, et cetera. And so you can easily see that as a shift in the spectra. And you might say, well, okay, then, just go out far enough and all your problems will be solved. Well, no, because the further out you go, the more trouble you're in from small decay constants and astro bounds. And also, if you go far enough out, then there aren't any cycles left that are small enough to give moderately weakly coupled gauge theories.
Sure.
And so the question that we found ourselves having to answer in order to carry out this work was, okay, we can't sit quite at the tip of the stretched Kähler cone because it's not always the case that there's a cycle that's the right size for QCD. So you need to go out a little bit. You need to go out to some intermediate distance where you can get at the green star, where you can get QCD, okay, where there's a cycle with size 25. And then what one wants to know is, in all the configurations where there's at least one cycle of size 25, how often are all the other cycles comfortably big?
Sorry, so how does this, so you were saying earlier that if you go inside this region where you have small cycles, that the strong CP problem is further alleviated. So I'm having trouble seeing how that's consistent with, when you get bigger cycles.
Absolutely. This was a point that confused us to no end. But the point is that region between between the red lines and the black lines there, the excluded region outside the stretched Kähler cone, but inside the regular Kähler cone. Okay, that has the property that some two cycles are sort of small. But the instantons that determine PQ quality are 4 cycles, or instantons wrapping 4 cycles. And so the question one has to ask is, if I populate this region, so now let's redraw this thing. And so now if I want to look at a point like here or something like that, then I do indeed have potentially a quite small 2 cycle. But we have to remember that we're not just interested in being at a generic point. We have to be at a point where there is a cycle of size 25. And so it turns out, this wasn't obvious, but it turns out that if you sample all these points around here and pick of them the subset in which there's a cycle of size 25, you tend to have even bigger hierarchies. And there's actually a way of understanding this that makes some sense, which is out here you've got really some big things and some small things. And if you're going to scale up a little bit to make at least one thing of size 25, you'll be left with even bigger hierarchies in various sizes. And so you'll be left with even more suppression of the QCD quality spoiling instantons. But yeah, this is, I should say, okay. In no way was this something that we ever thought we could exclude by that kind of a statement that I just made. When we started this work, we thought, oh, well, let's start at the tip of the stretched Kähler cone, scale out until something has size 25, see what we get, and then we'll worry about what happens outside the stretched Kähler cone. And we were really worried about it. It just, it so happens after you investigate it that one finds even bigger hierarchies closer to the walls. And so you find that the quality problem is even more ameliorated there. However, okay, and this is a critical point. I should have said this earlier. All the distributions I showed you for F and M are at the tip of the stretched Kähler cone modified to have one cycle of size 25. And all of those plots I showed at the end of the Cosmo and Astro bounds are at the tip of the stretched Kähler cone. If you go into these regions, those things will change. And so to give a proper answer for the Cosmo and Astro bounds, we will have to sample that full region, and we're engaged in that. But the only statement for which it's sufficient to look inside the red region is quality. For quality, it's enough to look here because things get even better for quality out there.
Thank you.
Okay, so well, if there aren't any other questions, then well, thanks to Liam again for taking the time to talk to us. It was very interesting, and well, we'll hear from you again in a couple of weeks, is it?
That's right. Yeah, October 18th. All right. Well, thank you so much. Really appreciate all the questions, and we'll talk again.
Thanks.
And let me add one more thing. we would love to hear from any of you about other constraints you think need to be incorporated, because all we did, we read the literature or whatever, but we thought, well, we should impose the coupling to 2 photons and the mf to the 4th dark matter constraint. But if there are other things that you think might be interestingly constraining, please send me a message. We would love to think about other kinds of constraints on this kind of stuff. All right. Cool.
Thanks.
Thanks. Bye-bye.